A viewer named Trey pointed me toward an unusual diagram and asked whether its geometry might share deeper relationships with GTEC instead of interpreting its symbols or history. We begin with a simpler scientific question. What happens if we ignore what the pattern is supposed to mean and examine only its geometry? Our first step is to remove the interpretation. Forget the names, symbolism, and proposed meanings. What remains is pure geometry. Points, lines, angles, intersections, and repeating structures. We are not testing whether the original symbolism is true. We are asking whether the underlying geometry contains measurable mathematical organization. Now we translate the geometry into mathematics. Points become nodes, connections become edges, and closed paths become cycles. The structure can then be represented as a graph and studied using adjacency and incidence matrices. What began as a visual pattern has now become a mathematical network that we can measure and compare. Next, we search for symmetry. Does the network preserve its relationships after rotation or reflection? Are some nodes mathematically equivalent? Graph automorphisms allow us to identify transformations that preserve the structure. Instead of simply saying that the pattern looks organized, we can begin measuring exactly how that organization works. Now we can address Trey's question more directly. We compare the extracted network with the GTEC dodecahedral wire network, examining conductivities, symmetries, cycles, topology, and spectral structure. But visual resemblance is not evidence. A meaningful connection would require measurable mathematical correspondence that survives objective comparison. Topology allows us to look beyond appearance. Imagine bending or stretching the network without cutting its connections. The shape changes, but some relationships survive. Conductivity, loops, and paths can remain invariant. These persistent properties may reveal more about the mathematical structure than the temporary shape we see. Closed loops are especially interesting. A loop follows connected relationships and eventually returns to its starting region. In the exploratory GTEC framework, we can test whether such cycles constrain deformation or support persistent geometric information. This is not yet an established physical result. It is a mathematical hypothesis that can be tested. Now comes the critical test, randomness. Humans can discover meaningful-looking patterns even in random systems, so we compare the candidate network with matched random networks. If similar symmetries and cycles appear just as often by chance, the pattern may not be special. A meaningful anomaly must survive this control test. We can now replace visual impressions with measurements, node degrees, cycles, connectivity, clustering, automorphisms, path lengths, topology, and spectral properties. Together they form a mathematical fingerprint. We can compare the chart, GTEC, and random controls using exactly the same tests. The question becomes quantitative. This is where Trey's question ultimately leads us from pattern to geometry. Network, symmetry, topology, measurement, and evidence. We are not claiming that this ancient diagram proves GTEC or predicts physics. We are building a way to test the idea and accept whatever the mathematics reveals. Trey gave us a question. Now we turn it into an experiment.